Okay, so this is lecture 9B, not 9A, but it goes with 9A. This is finishing up the example we started in the last uh, video where we were looking at recursively defined sequences and how to tell if they converge and figure out what they converge to. So we were looking at this sequence up here, recursively defined a1 equals 1, an plus 1 equals 4, minus 1 over an. And we notice that it looks like it's increasing, right? It looks like 3.66, 3.72, 72, 3.731, 731, so on down the road. It looks like it is increasing. And it looks like if all the ANs are positive, it looks like it should be bounded as well, at least by 4, if not by a smaller bound. So we ended last lecture pointing out that we should be able to tell that it is show that it's increasing and bound it. So let's try that. So first let's try showing it's increasing. Okay, so we're going to use what's called an argument by induction. And it's clear, we already know that A1 is less than A2, right? Because A1 is 1 and A2 is 3, and we know A1's less than A2. Acknowledging that's called the basis step of the argument. And the inductive step, the next part of this argument, I'm going to write this down, the inductive step, is showing that if we know for some k, some integer k, of course, bigger than or equal to 1, we know a sub k is less than or equal to well, we're going to prove strictly increasing, is less than ak plus 1, then necessarily ak plus 1 is less than ak plus 2. So let's just see why this would show that this is an increasing sequence. So this is k equals 1, right? K equals 1, we know A1's less than A2. We know that. Well, if this were true, if it's the case that this being true implies this is true, this would imply A2 is less than A3, right? But now just think this is k equal 2. We know that AK is less than AK plus 1, A2 is less than A3. That would imply, because we know this is true, A3 is less than A4. And so on down the road. That would imply A4 is less than A5, which would imply A5 is less than A6, and etc. Okay, so this is called an argument by induction. So let me erase this because we don't really need all these here in the way. Okay, so okay, we've already got the basis step, A1 less than A2. Let's suppose, okay, suppose that for some k, AK is less than AK plus 1. So let's just remember, what do we want? We want to show AK plus 1 is less than AK plus 2. Now the thing is, remember what AK plus 1 is. Remember that I missed something. Remember that AK plus 1 is going to be 4 minus 1 over AK, and AK plus 2 is going to be 4 minus 1 over AK plus 1. That fact's going to come into play. So let's go back to this. Okay, so we know AK is less, we're assuming AK is less than AK plus 1. So that's going to imply then that 1 over AK plus 1 is less than 1 over AK, right? You divide by a bigger number, you get a smaller thing than if you divide by a larger number, which is going to imply, this is assuming they're positive, but at this stage, we're up to this point, we've got it positive. So this is going to imply that negative 1 over AK is less than negative 1 over AK plus 1. And that's, well, when you negate things, you flip the inequality. And now if I add 4 to both sides of that inequality, I keep the inequality. So 4 minus 1 over AK is less than 4 minus 1 over AK plus 1. And, well, of course, that's going to imply that AK plus 1 is less than AK plus 2. And let's just make a note. We just noticed something. I actually needed that these are positive as well. Let's make sure we can confirm these are positive. We know this is positive and that's positive. And so we can assume, the basis steps, let's say this is true and this is bigger than 0. And let's say we know this is true and this is bigger than 0. Then we want to show this is true and this is bigger than 0. Well, the bigger than 0 part comes automatically because it's bigger than AK, which is bigger than 0. So that part's simple, and now we can assume these are both positive as well, and we get this. Okay, so let's now, so in other words, what we know is that this is an increasing sequence. In fact, it's a strictly increasing sequence. Of positive terms. Now, the fact that it's bounded by 4 now is now a little bit easier, because knowing that, well, it's still a slight inductive argument, but not too bad. We just have to note that each AN is positive. Actually, we don't even need induction. Each AN is positive, and so 4 minus 1 over AN. 1 over AN is also going to be positive, is going to be less than 4. So it's bounded above the sequence. Is bounded above by 4. Okay, so what is that? We've got an increasing sequence that's bounded above by 4, increasing and bounded above. What do we know about sequences of that nature? That implies there is a limit. It converges. So we know the sequence converges. We don't yet know what it converges to. But what we do know is that there exists an L, there is a finite L, such that the limit as n goes to infinity of AN is equal to L. But let's just think about this. If the limit as n goes to infinity of AN equals L, then what is the limit as n goes to infinity of AN plus 1? Well, as all this is saying is that n it gets larger and larger, A sub n is getting larger and larger as well. And this is saying it's going towards L, excuse me, as n gets larger and larger, A sub n is getting closer and closer to L. But this is just exactly the same sequence, just moved over one. So if A sub n's are getting closer to L, then A sub n plus 1s are also getting closer to L. It doesn't really matter where you start in that sequence when you look at the limits going to infinity. This has got to equal L as well. And this is for sequences. So that means, but what is AN plus 1? A sub n plus 1, of course, is 4 minus 1 over AN, right? So what that has is the limit as n goes to infinity of 4 minus 1 over AN. Well, on the one hand, that's equal to L, right? That's what we just showed. But on the other hand, we know where AN's going, and it's going to something bigger than 0, right? Because it's an increasing sequence. It's worth noting that L is bigger than 0. And this is 4 minus 1 over x is continuous at everything but 0. So this is going to 4 minus 1 over L. And we can use this equation to solve for L. So let's multiply both sides by L. So I get L squared is equal to 4L minus 1, right? Or, right, this is the equation, L equals 4 minus 1 over L. Or this is saying L squared minus 4L plus 1 is equal to 0. And using the quadratic formula, we can get L is equal to either plus or minus the square root of b squared 16, b squared, negative b, getting ahead of myself. Negative b, so let's get over here. L is equal to negative b, which is 4, plus or minus the square root of b squared, which is 16 minus 4ac. So 16 minus 4, which is 12, over 2a, that's over 2. So that's going to be 4 plus or minus 2 the square root of 3 over 2. Can it be, which is 2 plus or minus the square root of 3? So you think it's going to be minus the square root of 3? No, because we're getting closer and closer to 4, right? Or we're at least we're bigger than 2. So it's not going to be minus the square root of 3. So let's nix that right away. Our things are increasing, and the first one's 2, so the third one's 2. The third one's 3. Where are we? Let's go to the third term. And the third term in the sequence is 3. Therefore, 2 minus the square root 3 is going to be too small. But it looks like 2 plus the square root 3 is going to be it. And let's see exactly what that is. 3, let's see, clear. 3 square root. So that's 3.732. Look at that, 3.732 approximately. Approximately 3.732. Look at that. So it converges. It looks like it might be converging to 4, but it's not. Actually, when you look here, you can see it doesn't really look like it's converging to 4. It looks like it's converging to 3.7 something, but it could be going up pretty slowly. But in fact, it's converging to 3.732. We got it. Yay. Okay, we're done.